Good morning. It's January 29th, and this is your daily brief in science. Here's everything you need to know. Chinese scientists have achieved a significant milestone in genetic engineering by successfully creating laboratory mice with two male parents. This advancement marks a notable step in the field of unisexual reproduction. The findings were published in the journal Cell Stem Cell, detailing the manipulation of embryonic stem cells and the targeting of specific genes related to reproduction to produce bipaternal offspring. Researchers focused on editing 20 mammal-specific imprinted genes, which are known to restrict unisexual reproduction in mammals. This approach allowed some of the bipaternal mice to reach adulthood. However, the success rate remains low, with only 11.8% of viable embryos developing to birth. Many of the offspring experienced developmental defects, and those that survived to adulthood often exhibited stunted growth and sterility. Experts suggest that if this technique can be refined, it could revolutionize assisted reproductive clinics, enabling same-sex couples to have biological children together. The researchers specifically targeted imprinting genes to address historical challenges that have hindered successful unisexual reproduction in mammals. This study enhances the understanding of genomic imprinting's role in mammalian development and reproductive technologies, with potential implications for conservation and regenerative medicine. Despite these advancements, the bipaternal mice faced significant challenges, including craniofacial deformities and a shortened lifespan, which were attributed to excessive modifications of imprinted genes. Previous attempts to create bipaternal mice had failed due to issues with imprinting genes that limited embryo viability. The current modifications resulted in a higher success rate for developing animals and more stable pluripotent stem cells, paving the way for future research in this area. In 2024, the journal Science highlighted altermagnetism as a groundbreaking phenomenon, marking a significant advancement in the field of magnetism. This discovery was made by researchers at Johannes Gutenberg University Mainz, with experimental proof led by Professor Hans-Joachim Elmers at the DESY Research Center in Germany. The concept of altermagnetism first emerged in 2019 when JGU researchers observed unexplained momentum currents in antiferromagnets. This led to the proposal of a new type of magnetism that is now recognized as a distinct third type, alongside ferromagnetism and antiferromagnetism. While ferromagnetism involves magnetic moments aligning in the same direction, and antiferromagnetism involves them aligning oppositely, altermagnets exhibit neighboring magnetic moments that are anti-parallel, yet also show a spin-polarized current. The term altermagnetism reflects the alternating nature of the spin-polarized current's direction, as explained by Professor Jairo Sanova. This new form of magnetism has notable practical applications, particularly in enhancing data storage capacity by leveraging the magnetic moment of electrons. Researchers have identified at least 200 materials that potentially exhibit altermagnetism, suggesting broad implications for future research and technology. Support for this research comes from two collaborative research centers, CRC/TR173 and CRC/TR288, which received continued funding from the German Research Foundation in 2024. These centers focus on spin phenomena, emphasizing the importance of altermagnetism in advancing both scientific understanding and technological applications. A recent study has shed light on the lingering effects of COVID-19, revealing that nearly 2/3 of former patients continue to face health issues 2 years after their initial infection. This research, known as the Epidemiology of Long COVID, or EPILOC study, was conducted by the University Medical Center Freiburg and involved over 1,500 participants from several universities across Germany, including Freiburg, Heidelberg, Tübingen, and Ulm. Despite the official end of pandemic restrictions, many individuals are still grappling with the consequences of COVID-19, particularly the persistent symptoms associated with long COVID. Long COVID is characterized by health impairments lasting more than 4 weeks following a COVID-19 infection, with symptoms that may manifest during the acute phase or develop later. Common symptoms reported by patients include chronic fatigue, rapid exhaustion, memory problems, shortness of breath, chest pain, inner restlessness, depression, and sleep disturbances. Notably, around 12% of patients reported experiencing chronic pain, while the study also indicated a decline in grip strength, maximum oxygen uptake, and respiratory function among those suffering from long COVID. Researchers have suggested that these ongoing symptoms may be linked to alterations in nerve and metabolic function interactions, as well as persistent inflammatory reactions. Virologist Christian Drosten highlighted that approximately 6% of COVID-19 patients experience long COVID symptoms, emphasizing the widespread impact of this condition. Study leader Winfried Kern expressed concern over the significant number of patients facing limitations 2 years post-infection, and he emphasized the need for systematic long-term follow-up and medical examinations. Kern also pointed out the importance of identifying factors that influence recovery from long COVID to develop effective therapeutic interventions. The study demonstrated that functional parameters such as hand grip strength and oxygen consumption during exertion deteriorated in long COVID patients compared to a control group, significantly affecting their quality of life. Published in the journal PLOS Medicine, this long-term study highlights the ongoing impact of long COVID on individuals, even as the world moves past the peak of the pandemic. A groundbreaking development in quantum physics education is taking shape at the University of Barcelona. A research team has created experimental equipment aimed at helping undergraduate students better understand complex concepts like quantum entanglement and Bell inequalities. This innovative equipment enables students to directly measure quantum entanglement, which significantly enhances their grasp of these intricate phenomena. Bruno Julia Diaz, a co-senior author of the project, highlights the critical role that hands-on experiments play in teaching these advanced topics. Student feedback has been overwhelmingly positive, with the equipment integrated into both bachelor's and master's degree courses. This integration is improving students' practical understanding of quantum mechanics. Notably, the system is designed to be cost-effective and versatile, making it suitable for various educational settings, including those with limited resources. Quantum entanglement is essential for the development of advanced technologies, including quantum computers and secure data encryption. Currently, the field of quantum physics is undergoing a second revolution, driving advancements in computing, telecommunications, cybersecurity, and biomedicine. In recognition of the importance of quantum science, UNESCO has declared 2025 as the International Year of Quantum Science and Technology. The research detailing this equipment was published in the journal EPJ Quantum Technology, showcasing collaboration among professors and students, including Bruno Julia, Martí Duocastella, José M. Gomez, and master's student Raúl Lahoz. This new system allows students to prepare various quantum entangled states while enhancing the photon capture process using fiber optic detectors, which streamlines experiments and improves detection efficiency. The concept of hidden variables in quantum entanglement, proposed by Einstein and others in 1935, was later challenged by John Bell in 1964, leading to significant advancements in our understanding of quantum mechanics. In 2022, Nobel laureates Alain Aspect, John F. Clauser, and Anton Zeilinger were recognized for their pioneering work in quantum information and entangled photons, underscoring the significance of this evolving field. Researchers have made a groundbreaking advancement in molecular evolution by simulating 500 million years of protein development using an AI model named ESM3. This innovative approach has resulted in the creation of a new fluorescent protein called ESM-GFP, which acts as a marker under ultraviolet light. The primary aim of this research was to generate a novel green fluorescent protein. ESM3 operates by mimicking the evolutionary process, enabling it to produce proteins that have never existed in nature, including the distinctively bright ESM-GFP. To achieve these results, ESM3 was trained on a massive dataset consisting of 771 billion tokens derived from 3.15 billion protein sequences. The model functions similarly to completing sentences, filling in gaps in protein blueprints to generate previously unknown proteins. The sequence of ESM-GFP shows only 58% similarity to the closest known fluorescent protein, requiring 96 genetic mutations to evolve. This process, which would have taken over 500 million years in nature, highlights the efficiency of ESM-3. While experts recognize the model's potential to accelerate protein engineering applications, they note that ESM-3's simulation of evolution is limited to individual proteins and does not encompass the full complexities of natural selection. The model is available to the scientific community, enabling researchers to engineer proteins for various applications, including solutions for environmental issues like plastic waste degradation. Launched in mid-2024 by Evolutionary, an AI startup founded by former Meta engineers and supported by major tech companies such as Amazon and NVIDIA, ESM-3 is a multimodal generative language model designed specifically for biological data. The creation of ESM-GFP is contributing to ongoing discussions in evolutionary biology regarding determinism versus contingency. Future iterations of ESM-3 are expected to enhance its capabilities, potentially leading to innovative solutions for global challenges. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.